All right, hi physics class, Mr. Mellinger, and we're doing a lesson for 2 days actually, Thursday and Friday. So this will finish up week 2 of distance learning, and it is on buoyancy, which is why things float. So let's go ahead and get started, and it's take about a half hour, and I'll do most of the problems with you, and then there's a few I'll leave for you to do on your own. Okay, so why does a large ship float and a nail sink? Students answer this question by saying that the ship has air in it. And this answer is partially correct, but it does not explain why the air makes the ship float. There are 2 explanations for why some objects float and others sink, and one of these is several thousand years old. The ancient Greek scientist Archimedes proposed the following explanation. An object will sink in water until it has displaced a weight of water equal to the object's own weight. So in this unit, we can use the terms weight and mass interchangeably. Basically how much force or weight, mass, something puts down on something else. And the word displace, just know what that means. It means take the place of or push out of the way. So it pushes water out of the way when you put that object in it. The second explanation was developed at a later time, and it's the density rule. And it says that an object that has less density than water will float, while an object that has a greater density than water will sink. So, while these explanations sound different, they are really the same. First, let's define density. Density is mass divided by volume. A plain way to state this is that density is how much matter, stuff, or mass you have crowded into a certain amount of volume, which is space, how much space it takes up. So if you look at the soccer ball and the steel ball below, they might both have the same mass, but the mass of the steel ball is packed into a smaller amount of volume, of space. So assuming that they're both about 4.45 kilograms, which is typically what a soccer ball weighs, just about that. The diameter across the soccer ball is 0.07 meters, but the diameter across the steel ball is only 0.02 meters, much smaller. So even though they have the same mass, they weigh the same, the steel ball is said to be more dense. So both of the balls have the same mass or weight, and we will use the term mass in this assignment, but the mass of the steel ball is packed in a smaller volume. So the steel ball has greater density. The concept of density is defined in physics around the properties of water. And it's this. This is the relationship. 1 kilogram of water equals 1 liter. And a kilogram is about 2.2 pounds. And you know what a liter is. You've bought soft drinks that are liter bottles, so you have a sense of that is. So this states that 1 kilogram of water mass occupies a volume of 1 liter. This is not just a coincidence. Density was defined this way in science. This means that when you buy a 1 liter bottle of water at the store, it has a mass of 1 kilogram. So below we have water in a swimming pool. So look at the diagram on the left. We have water in a swimming pool, and we've drawn an imaginary box around 1 liter of that water. Remember, this is really 3-dimensional, even though what you're looking at is a 2-dimensional image. You got to remember a liter is a 3-dimensional volume. So we'll imagine that's a cube that has a volume of 1 liter. So if you look at that, we've put an imaginary box around 1 liter of water, and since it's water, we know that 1 liter equals 1 kilogram. So inside of that box is 1 liter and 1 kilogram. So below, let's read this. Below, we have a box that represents 1 liter of water, which is 1 kilogram. The arrows represent the water below the liter box that is holding the liter box in place. So think about it. Just think of this as a box of, it could be anything. Gravity's going to pull it down with a certain amount of force. Since this box of water is not moving down, it means that the force of the water underneath it that it's pushing up on, think of it like a tabletop, is pushing an equal amount of force upward as the amount of force that gravity is pulling this box downward with. And since the box is not moving down, it has to be an equal amount of force down. That's our balanced forces. Let's continue to read this. The arrows represent the water below the leader box that is holding the leader box in place. Since the leader box is not moving, the arrows must be pushing up with the same amount of force that the 1 liter kilogram box is pushing down due to gravity. And those are balanced forces, which we talked about in class. So the water's just going to sit there and stay in one place. Now let's go over to the diagram on the right. What if we replaced the box of water with a wood block that was the exact density of water? It's 1 liter in size, in volume, and it's 1 kilogram in mass. The arrows below would not know or care if they are pushing up on water or wood. All they know is that whatever is above the arrows has a mass of 1 kilogram and occupies 1 liter of volume. So you can just replace this with for this, and they're still going to support it exactly the same way they would if it was water. They don't care what the material is. It's a certain amount of mass contained in a certain amount of volume. So the situation in the diagram means that a block that has the same density as water will sink until it exactly takes the place of the same mass and same volume of water. That's what this has done. It has the same mass and the same volume of the water, so it sinks until it takes the place of the same mass and same volume of water. This is what Archimedes said would happen. So what he said is this block will sink until it displaces a weight of water. In this case, we're talking about a mass of water, 1 kilogram, that's equal to the mass of the block. So it displaced 1 kilogram of water. It is 1 kilogram, so it displaced 1 kilogram of water. And since both volumes are a liter, it happened to take exactly that liter of volume that the water had occupied. So that means that the block of wood is going to sink until the top of the wood just touches the top of the water. So this is what Archimedes said would happen. It also means that an object with the same density as water will sink until the top of the object just touches the top of the water. Then it will stop sinking. Okay, so now let's come up with some rules to determine how far an object will sink. So here are the rules for determining how far the object will sink. First, determine the mass of the object. Then you're going to say whatever that mass is, you want to have the same mass of water because the object is going to displace an equal mass of water as its own mass. So determine then, once you've determined the mass of the water, determine how many liters of water is equal to the mass of the object. And then you place the object far enough down in the water so that it takes up that many liters of water. So let's take an example. It's the easiest way to learn this. So example, place the box on the left, this box right here, in the dashed boxes in and above the water so that it displaces a mass of water equal to its own mass. That's Archimedes' principle. So we look at this. This box has a volume of 2 liters. It takes up 2 liters of space. You can see it's twice as big as one of these boxes, which are 1 liter. And it has a mass of 1 kilogram. So if it has a mass of 1 kilogram, Archimedes says it's going to displace 1 kilogram of water. So if we look down, this is the water level, and 1 kilogram of water would be one of these boxes right here. So I'm just putting a box around how much water this box is going to displace. And there it is. 1 kilogram displaces 1 kilogram. So the box is going to take up this square right here. Okay? But notice the box is not just the same size as this square. It's twice as big as this square. So if we break the box into 2 1-liter sections, there's 1 liter, there's 1 liter because it's a 2-liter box, then what happens to that other liter? One of the liters fits in here. What happens to the top liter? Well, it sticks out above the water. So I'm going to go ahead and draw a box around this 1-liter box that's up above the water. Notice this is not 1 kilogram, but it is 1 liter because it's air. Okay, and that's what the box would do. The box would sit, it would displace 1 kilogram because it is 1 kilogram, but since it's 2 liters in size, only one of those liters can fit down below the water. the other one's going to have to stick up above the water. So there's an exact duplicate of that box right there. And there it is, I drew it over there. So the box has a mass of 1 kilogram, so it sinks until it displaces 1 kilogram of water. This equals 1 liter of water. Since the box has a volume of 2 liters, 1 liter of the box stays above the water. So there you see what I drew over there. Now, so what's the density of the box? Well, the density of water is 1 kilogram for every 1 liter. That's what each of these boxes up here, or each of the boxes down below the water say. 1 kilogram for every 1 liter, so that's 1 kilogram per liter. That's the density of water. The density of the block, or box, sometimes I call it a block, sometimes a box, is 1 kilogram, and it's 2 liters in volume. So 1 divided by 2 is 1/2, so it has a density of 1/2 kilogram per liter. So you saw how this obeys Archimedes' rule in that the box displaces a mass of water equal to its own mass. Now you're seeing how it obeys the density rule. The density of water is 1. The density of the block is 1/2. So since the density of the block is less than the density of water, it will float. It will float. Okay, so let's read that. So the density of the box, 1/2 kilogram per liter, is less than the density of water, which is 1 kilogram per liter. So 1 liter of the block sinks below the water because the 1 kilogram mass of the entire block displaces 1 kilogram of water. But since the block has 2 liters of volume, 1 of those liters sticks up above the water. So that's what we're seeing. Now, here's something else to notice. This is interesting. Also notice another fact. The density of the block is equal to the fraction of the block that is below the water, which is to say 1/2. So if we look at the density of the block, it's 1/2, and you look at that 1/2 of this block is below water. There's half of it down there below the water. So the fraction of the block that's going to be below the water is equal to the density of the block. Okay, and you're going to see that in some further examples. Okay, so up at the top it says now it's your turn. And I'm actually going to do most of these with you. So let's go ahead and do these together. So I'm giving you this template here, and there's your box. So box number 1 is 2 liters and 2 kilograms. So Archimedes' rule says that this is going to displace 2 kilograms of water. If it's 2 kilograms, it's going to displace 2 kilograms of water. Well, how much is 2 kilograms of water? Well, there's 1 and there's 2. So 2 kilograms of water is the water that's in these 2 boxes right here. This is 2 kilograms of water right there. And I can draw a line all the way around. Okay, so it takes up 2 kilograms of water. And we also see that those 2 kilograms of water are 2 liters of water. 1 liter there, 1 liter there. So that means our 2-liter box is going to fit exactly in there. So it also is going to sink until the top of the box just touches the top of the water right there. Let's do a couple quick calculations. The density of the block is 2 kilograms for every 2 liters. But you can reduce that fraction down to be 1 kilogram per liter. And we know that, okay, and that's also the density of water. So that explains why it just sinks until the top of the box touches the top of the water. In other words, this 2 kilogram, 2 liter block basically just perfectly replaces the water that was there. It has the same mass, it has the same volume. So it replaced 2 liters and 2 kilograms of water. Now, what fraction of the block is underwater? Well, the whole block. So 1 out of 1 is the fraction, or 1. So the entire block is underwater. So notice this number is the same as the density. Okay, let's do another one. So now over here, box 2, we have a 3-liter block, and it has 2 kilograms of mass. So the first question you ask is, first thing you observe is, it's going to displace 2 kilograms of water. So let's go over here, and where's 2 kilograms of water? Well, this box contains 1 kilogram, and this box contains 1 kilogram. You add those together, you have 2 kilograms. So that means this block is going to displace this much water because it's 2 kilograms, and it's going to displace 2 kilograms of water. So there you go, it's going to take up these 2 blocks. But this is different than the last one. This block has 3 liters of volume, not just 2. So you can't fit 3 liters of volume in here. You can only fit 2 liters. Each of these boxes represents 2 liters of space. So where does that 3rd liter go? It has to go up above the water. So here it is up here. So that's how this box would sit in the water if it's 3 liters volume and 2 kilograms of mass. So let's calculate the density down here. So the density is 2 kilograms of mass crowded into 3 liters of volume, which equals 2/3 kilogram per liter is the density. Now, what fraction of the block is underwater? Well, look at this. There's 3 boxes. This block fills up 3 boxes, and 2 of them are underwater. So that means 2/3 of the block is underwater, and you'll notice that's the same as the density. Same number as the density. Okay, this isn't too hard. Let's do another. In fact, I'll do 3 more for you here, and I'm going to leave about 3 of them for you to do. You should be able to do these in about 2 minutes. It should be easy. Okay, here we go. Box number 3 is 3 liters in size, the same as the last box, but it's only 1 kilogram in mass. So what do you ask yourself? You say, how much is 1 kilogram of water? It's going to displace 1 kilogram of water. So where do we find 1 kilogram of water? Well, it's the first box down is 1 kilogram. So that box right there. So it's going to displace that much water. And that represents 1 liter. But this box is 3 liters. So where do the other 2 liters go? They sit up above the water. So they're up here and over. So they sit up above the water, like that. So the box is displacing a kilogram, 1 kilogram, 1 kilogram. It's displacing its weight in water. That's Archimedes Principle. But it has 3 liters of volume. 3 liters can't fit in that square, so the other 2 have to fit up above. Okay, so let's do the calculation on that. The density of the block is 1 kilogram for every 3 liters, which equals 1/3 kilogram per liter is the density. And if we look at the diagram, 1/3 of the box, there's 3 boxes here, and one of them is below water. So 1/3 of the box is below water. The fraction below water is 1/3, and that again is the same as the density. All right, try this one. See if you can do these on your own now. Okay, box number 4 is 4 liters and 3 kilograms. Okay, so that means it's going to displace 3 kilograms of water. So 3 kilograms of water, there's 1 kilogram right here, there's 2 kilograms, there's a 1/3 kilogram. So it's going to fill up all 3 of these boxes. By the way, don't assume that this is the bottom of the swimming pool. That's just the bottom of the boxes I drew. The bottom of the swimming pool could be much lower than this. Okay, but 3 kilograms is going to be this. That's how much 3 kilograms of water would be these 3 boxes. And that constitutes 1, 2, 3 liters. But this block is 4 liters. It has 1 more liter than this, so that 4th liter is going to sit up above the water. And it's going to take up that. Okay, so the density of the box is 3 kilograms for every 4 liters, which is 3/4 kilograms per liter. And what fraction of the box is underwater? Well, you have 1, 2, 3, 4 liters there, and 3 of them are below water. So 3/4 is the fraction of the box that's below water, and that again is the same as the density. Okay, I'm going to do one more for you. All right, So I'm going to leave the problems on the next page here for you to do. They shouldn't be too hard if you understood how we did the first set of problems. Now I'm going to go on to one more. It's a little bit different. So we're going on to the last page. And let's look at the example over here on the left. So you have a box. It's 1 liter and it has a mass of 2 kilograms. Okay, so let's read what it says down below. This is a different situation. So something happened here. The block, let me go ahead and raise this so you can see the whole thing at once. Okay, so it says something happened here. The block is 2 kilograms and sinks until it displaces 2 kilograms of water. So that means it would have to sink until it displaced this much water, because 2 boxes of water is 2 kilograms. So the block is 2 kilograms and sinks until it displaces 2 kilograms of water, which equals 2 liters of water, this much. But the block can never occupy 2 liters of water because its volume is only 1 liter. So if it's going to sink until it occupies 2 kilograms, it would be this much. And that's 2 liters of water. But look, the box isn't 2 liters big. It's only 1 liter big. You're not going to put it in the water and have it suddenly grow. It's going to stay whatever size it is. It's going to stay that size. So what does that mean? It can never occupy 2 kilograms of water. It has a mass of 2 kilograms, but it can't occupy 2 kilograms of water because that would be this much water that I'm tracing out with the pencil, and it can never occupy that much water. It can occupy it just can't do it. It's not big enough. So that means it's going to sink until it occupies a weight of water that's equal to its own weight, but it can never do that. Therefore, it's just going to keep sinking and sinking and sinking until it hits the bottom of the pool. So the block sinks to the bottom. So let's look at the density of the block. It's 2 kilograms and it takes up 1 liter. So that's 2 kilograms per liter of density. 2 kilograms per liter is greater than the density of water, which is 1 kilogram per liter, so the block sinks. So using both Archimedes' rule and the density rule, that block is going to sink. Let's take a look at this. So let's say you put the block in, and at first, because it's this big, it occupies this much space. And remember, the water underneath this block right here, before you put this box in, is pushing up. And that water, think of it as a weightlifter. And that weightlifter can hold up 1 kilogram of water. That's what those arrows are capable of holding up. They can't hold up more than that. If they were pushing up with more force than the amount of force of 1 kilogram pushing down, they would be pushing this block of water upward, but they're not. They're holding it still, which means they're pushing up with exactly as much force as it takes to support 1 kilogram. So if all of a sudden you put 2 kilograms there, it's like giving a weightlifter more weight than he can lift. All of a sudden you throw that weight on top of him, and it's going to fall. The 2 kilograms, because this water can't hold that up. So let's say it falls down to here. It wants to occupy an amount of water that is 2 kilograms in mass. So it falls to here. What happens here? Well, this water right here that's pushing up right at this point, it can support 2 kilograms. Why? Because 1 kilogram of water and 1 kilogram of water is 2 kilograms of water. In this big block right here, that's 2 kilograms of water. So yes, this water right here that's pushing up is capable of supporting 2 kilograms. Here's the problem. When that block gets to here, then right here you have a 2 kilogram block occupying that box right there. Problem is, that's not the only thing that's there, that's pushing down on this water right here. What happened up here? This space doesn't just stay blank. Water comes in from both sides and fills it in, so that you now have another kilogram of water right there. So right here is 1 kilogram of water. So you have a kilogram of water and a 2 kilogram block pushing down this way right there. And you have water that's capable of supporting only 2 kilograms. So 1 plus 2 is 3. So you have 3 kilograms pushing down, and you have only water that's only capable of holding 2 kilograms pushing up. Therefore, the block is going to continue to sink some more. And it will, in fact, sink all the way to the bottom of the pool. So this one's a little harder to understand maybe than the one where they floated. But just understand it's more dense than water, and therefore it's going to sink in water. It can never occupy a volume that contains its own mass, 2 kilograms. It can never do that because it's not big enough to occupy 2 kilograms. Okay, so that takes care of that. You do this problem over here. Density of block, fraction of block underwater, does a block float or sink? And then I want you to answer this question. It's a question I asked at the beginning and I never gave you an answer. I want you to think about it. Using the concept of density, think of the density of steel and the density of air. Explain how a large steel ship can float. Just give that about 4 sentences. You don't have to use any numbers or calculations. Just explain in concept how a large steel ship can float. Okay, so that's the end of your assignments for the second week. And if I haven't seen any assignments from you, I'm going to be in touch with you in the next couple of days and need to be sure you stay on top of this. It's a real easy class to get an A in if you'll just do a little bit of work each week. So I'll be in touch with some of you and maybe all of you in the next few days. Okay, so you have a good weekend. Be well. Take care of yourselves and your family. And I'll see you on Monday.